In this video, our goal is to find some basic techniques for finding general antiderivatives of functions. To begin with, let's just remember that if I find a function whose derivative is g, then the antiderivative of g is that function plus a constant c. For example, the derivative of x squared over 2 is equal to x, and therefore the antiderivative of x is x squared over 2 plus c. The derivative of e to the x is e to the x, and so the antiderivative of e to the x is e to the x plus c. Again, the derivative of sine x is cosine x, and so the antiderivative of cosine x is sine x plus c. And the derivative of negative cosine is sine x, so the general antiderivative of sine x is negative cosine x plus c. We have a constant multiple rule which works exactly the same way as it does for derivatives, and this is very helpful in computing antiderivatives. For example, if I want to find the general antiderivative of 3 cosine x, then I can pull that 3 out front and just focus on the derivative of cosine x for a while, and that's sine x plus c, as we just discovered on the previous slide. And now I just distribute this 3 to sine x and to c. But you'll notice that since c can be any number, then so can 3c, so there's really no problem with just writing 3 sine x plus c. In fact, you can think, since the derivative of 3 sine x is 3 cosine x, then 3 sine x is an antiderivative of 3 cosine x, and so the general antiderivative is obtained by simply adding a c to that. Okay, next we have a sum rule, which again works exactly the way it does for derivatives. You can focus on computing an antiderivative term by term. In other words, I can take this function, e to the x plus sine x, and compute this term by term. I can write it as 2 separate integrals. And we've already done both of these integrals. The integral for e to the x is just e to the x plus some constant c, and the integral for sine x is negative cosine x plus another constant. Okay, let's rearrange these terms, and notice that since C1 and C2 are both just arbitrary real numbers, their sum is again an arbitrary real number. So we can replace C1 plus C2 by just a single constant C. Okay, let's try to develop a formula for the integral of x to the n. Well, we know that the derivative of x to the n plus 1 is n plus 1 times x to the n, which is almost telling us the antiderivative for x to the n, except for this n plus 1 is here. So if I divide by n plus 1, then I notice that the derivative of x to the n plus 1 over n plus 1 is just x to the n. That n plus 1 would come down and cancel with this n plus 1 down here. Okay, this was only legal to do if n was not equal to negative 1, by the way. But now this line here tells us that if n is not equal to negative 1, then the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. Okay, this is our first integration formula, and it's basically telling us that to integrate powers of x, you take the exponent and bump it up by 1, and then divide by that new exponent. Let's see how this works in the context of polynomials. The sum rule allows us to rewrite this as a sum of 3 separate integrals, and then the constant multiple rule allows us to pull those coefficients out front of each individual integral. And by the way, when I write integral of dx, I mean integral of 1 times dx. It's just the constant function 1 there. Okay, now let's perform the power rule for each of these integrals. This is x to the 2, so we bump that exponent up by 1, and then divide by that new exponent to get x cubed plus 3. Similarly, x to the 1, this will become x to the 1 plus 1 over 1 plus 1. And x to the 0 becomes x to the 1 over 1. I haven't written the 1's there, but that's I mean, you can even say, well, the derivative of 5x is clearly just 5, so that's the correct antiderivative there. Okay, all that's left to do now is to simplify. Okay, this integral is going to be a little bit trickier because it's not already in the form where we're going to be able to use the power rule. It's not just t to a power. Instead, it's some complicated expression of t squared minus 2 raised to a power. So before we can do anything, we're going to need to rewrite this integral. Let's multiply out this binomial, and now we have a polynomial in standard form, which we can use the technique from the previous example to do. right? I mean, now we can use the sum rule to split this into 3 separate integrals and compute them term by term. So let's do that. We're going to use the power rule on each term. So we bump the exponent up by 1 to 5 and then divide by 5. We bump this exponent up by 1 to 3 and divide by 3. And this is 4 times t to the 0, so we bump that 0 up to 1, so t to the 1 now, divided by 1. In this example, we're also going to need to rewrite the integral. You'll notice that this fraction does not resemble any integration formula that we know of, but we do have a numerator which we can split up into 2 fractions. And each of these fractions can be simplified and written in fractional exponent notation like this. And now each of these terms can be computed by using the power rule that we discovered a while ago. So we'll bump the exponent up by 1. 1/2 plus 1 is 3/2, and divide by that new exponent 3/2. And negative 1/2 plus 1 is positive 1/2, and we divide by that new exponent 1/2. And now these are 2 compound fractions, which can be simplified by multiplying top and bottom by 2. And so this is what we get. Okay, let's see what to do about the integral of x to the negative 1. Remember, this power rule that we've developed is not valid for this situation. We would be dividing by 0 if we tried it. So how do we come up with a derivative, or antiderivative, of 1 over x? Well, we know that the derivative of natural log of x is 1 over x, so you might think that natural log x is the antiderivative. But there's a problem with this. You see, the function natural log of x is graphed here in black, and its derivative is shown here in purple. It's 1 over x for x greater than 0. But this is slightly different from the function whose antiderivative we're seeking. The full function 1 over x also includes this blue portion. And so the full general antiderivative of 1 over x should include a part to the left of the y-axis. So let's see if we can be creative and find a way to do this. If we reflect the natural log function over the y-axis, that means multiplying the x by negative 1, then we get this graph. And let's see what its derivative is. Using the chain rule, we find that the derivative is just 1 over x, which tells us that yes, natural log of negative x to the left of the y-axis is also an antiderivative for the left side of the function 1 over x. So if we can combine them into a single function, this is done by just making it natural log of absolute value of x, then we have the full general antiderivative for 1 over x. Now, it's not really important necessarily that you understood that in that full discussion there, but you certainly do want to remember this general antiderivative formula, and just remember that it does come with an absolute value sign around the x. Now, just like when you were learning to differentiate, you had to learn some derivative formulas, you're going to have to learn some integral formulas for integration. But the good news is that you've already memorized most of these formulas. It's just in a different form. For example, you already know that the derivative of tangent x is equal to secant squared of x, which means that the antiderivative of secant squared x is tangent x plus c. And similarly for the rest of these formulas. You've already memorized them in another form, you just need to be able to reinterpret them in this new context. Now, it's important that you keep the power rules for differentiation and integration straight in your head. You see, integral power rule tells you to bump the exponent up, whereas the power rule for differentiation tells you to bump the exponent down. So make sure you're getting those not mixed up. Also, make sure you remember this absolute value sign that must go around this x when you're taking the antiderivative of 1 over x. Okay, to recap, we have a constant multiple rule and a sum rule at our disposal, and these work exactly the same as they do for differentiation. And I want to issue a warning here. We can't compute the integral of a product of 2 non-constant functions one factor at a time. It's more complicated like it was in the case of differentiation, where you needed the product rule. So we're going to develop a technique for products of functions in section 5.6. Okay. Well, next, remember that you need to know these integration formulas. And again, you've already memorized them in another context. You just need to be familiar with them enough so you can read them backwards, and you can tell the antiderivative of these functions that were involved in your differentiation formulas. we've encountered our first integration technique, which is to rewrite the integral before integrating. If you can rewrite your integral in a more simplified form, then you have a better chance of recognizing some applicable integration formula. In the next video, we're going to discuss some new notation which is going to be needed in section 5.1. So this will be slightly off topic, but it's a necessary digression. But for now, see if you can come up with the general antiderivatives of these two functions. And remember that you should probably rewrite the integral before trying to compute the integral. You may need to do some distribution, you may need to rewrite in fractional or negative exponent notation. So give that a try, and I'll see you in the next video.